So we're going to test whether or not there's a difference between September and April weights by using the sign test. So when we subtract those two and get a difference, we're not going to look at the magnitude of that difference. What we're going to look at is the sign of that difference and test whether or not the difference tends to be in the middle. That is, half the time you're above zero, half the time you're below zero, or is there a preponderance of one or the other? So essentially, we're going to test this hypothesis that the median difference is zero versus the median difference is something other than zero. And here I'm using eta to represent my median. Other books do different things. That's okay. And looking at the data, we have to throw out anything that turns into a zero because that's not positive or negative. So you're losing some of the data right off the get-go. If you then count the number of positive signs, I got 2. Number of negative signs, I got 7. Your test statistic, in this case, when the number of pieces of data you have is so small that it is less than 25, your test statistic is going to be just the smaller of these two numbers. So in our case, it's going to be x is 2. Now let me look back at our hypothesis test. So if n is less than 25, then x is your test statistic. That is, x is the number of the less frequent sign, either plus or minus. If x is your test statistic, then you're going to go to table A7. Well, that's really inconvenient. All of a sudden, you got to go to this table. And here's that table. And you got to figure out, are you doing a one-tail test or a two-tail test? You got to figure out what n is, et cetera. And then pull out the correct test or critical value for your sign test. Fortunately for us, StatDisk will do that for us. But the thing to keep in mind, the important thing is that you're going to reject H0 if the smaller number, if your test statistic is less than or equal to the number that you get from this table. So let's see what we're going to do here. Let me go back to StatDisk. There's your critical value. Here's our test statistic. You're going to reject H0 if the test statistic is less than or equal to the critical value. So,
Reject.
Is 2 less than or equal to 1? So if the test statistic is less than or equal to the critical value, then reject. Reject H0. Geez, reject H0. So our test statistic was 2. The critical value was 1. So
Fail
are we
to
going to
reject.
reject? Yeah, fail to reject. Yeah, we just didn't have enough oomph to reject in this case. So fail to reject. And I always like to put H0 because some people want to fail to reject HA, which isn't correct. Yeah, fail to reject. Cool. And that's it. So it's not a really hard test, but what is a little bit different for us is that we're not used to dealing with something other than the p-value. So that is a little bit of a change for us. It's also going to change when we have a higher value of n. We're also going to have to learn how to do things more like we did old school. So that is by setting up a rejection region and a fail to reject region. As for this one, we fail to reject H0. So that's step 5. Are you okay with this? Here was our test statistic, test stat, and here is our critical value. So we fail to reject. let's put that into words. I mean, it's not something that you're going to be facing in the homework, but it's good to practice. Because eventually, the idea is that you're going to use this someplace outside of a stat class, and you have to communicate your ideas. So for step 6, I'd say something like this. The data failed to provide sufficient evidence to reject the claim Now, which claim is it that we're failing to reject? Well, it's the null hypothesis so the null hypothesis was of a median difference and here you might want to note that it's September minus April. Fail to reject that claim that the median difference is equal to 0. Meaning that half the time you're above, half the time you're below 0. So that 0 is actually in the middle. 0 is your median difference. Okay. There's your first one. Any comments, thoughts, or follow-up on that one?
No.
All right. Now, one of the problems with this test is just how much information you're throwing away. Let's look back at it, and I want to understand or help you understand something called efficiency. So let's go back up here to advantages and disadvantages. Some of the disadvantages are that non-parametric tests tend to waste information. And we can see that when we look back at the previous example. We started out by throwing out what happened here at 0. Well, that's not good. So you're throwing away 1/10 of your data. Okay, so let's look at that go for a second. The other part of the problem is that we threw away the magnitude of these differences. I mean, there's a huge difference between a loss of 1 pound and a loss of 8 pounds. That's a pretty big difference. You could lose 1 pound just by not eating so much salt in your diet. You know, having a day where you didn't eat a whole lot of salty meals, you'd probably lose at least 1 pound. So that magnitude is lost. When you're working with the sign test, it's all, okay, was it positive or negative? This could have been negative 18 pounds, which would be pretty significant. It might even sway the data from fail to reject to reject. But all those differences, the magnitudes are being thrown out. So sometimes these tests aren't as powerful as the fancy word, but a probably more realistic or easier to relate to term is they're not as efficient. And so let me define efficiency for you, the efficiency of a non-parametric test. And this is something that I'd want you to know coming away from this section. Is the efficiency is the number of observations you require by a parametric test divided by the number of observations required by a non-parametric test. So let me write that down as soon as I find the right pen. Number of observations required by a parametric test. Those are the ones that we did in chapter 8, our t-test, our, well, we did a z-test for population proportions, et cetera. I'm going to compare the number of observations needed for a parametric test to the number of observations needed by a non-parametric test. So number of observations required by a non-parametric test. And so far, you only know one non-parametric test, and that one non-parametric test is called the sign test. The sign test isn't very efficient at all. It's actually kind of really poor on the efficiency scale. Well, I'll give you a chance to copy this down here before I flip to the page that shows the efficiencies, and it's on one of your handouts. Should have been something about advantages and disadvantages of your parametric test. So this table right here talks about your efficiency ratings, and you see the efficiency of the sign test is pretty weak. It's 63%. So that means if you were testing in section 9.3 for matched pairs, you had some data that satisfied all the requirements, you'd only need 63 observations to be able to reject the null hypothesis in that situation. Whereas if you had the sign test and you're trying to, again, reject the hypothesis like the median difference is 0, you need 100 observations. So, wow, that's not too good. Its efficiency isn't that great, but you know, it is what it is. The nice thing about the sign test is you can apply it in places that you can't apply the test from section 9.3. When I was in college, earning my master's degree, I was pretty down on non-parametric tests. I never took the class. I'm like, ugh, waste of time. I always use a parametric test. But I've changed my attitude on that. If you look at the efficiencies of some of these parametric non-parametric tests, 95%, 91%, those are really good. And the thing about it is that a lot of times your assumptions for these parametric tests just don't hold up. You don't have a normal distribution. You don't have 30 observations, et cetera. It's not a chi-square. It's not an F distribution. So there's a lot of tests that really shouldn't be run. If you don't satisfy the requirements, don't run the test. But these tests are easy to meet. Your non-parametric tests have very, very relaxed requirements. So I think they're underappreciated, personally. Hopefully you're getting a good idea of what efficiency is. That's something that I wouldn't mind testing you on a little bit further. Let's do another example. This one's example C. And you're being asked to test the claim that there's a difference between the actual and reported heights for 12 to 16-year-old boys. And I think I sent you a link on that. If you don't have your email handy, let me see if I can't find that link for us. I'll put that in the chat. You can copy it. There you are. So you can grab your own copy of this data. So you've got the reported height and the actual height. And while you're opening this up and copying it, well, actually, maybe I'll save it till after our test is done. But what we're going to look for using the sign test is not the actual difference, which is in column C. It's the sign of that difference. Now, when I subtracted here, what I did was I went through and I said, okay, I'll put down 0 if the distance is negative, if the difference is negative, and 1 if it's positive. Now, what's the advantage of doing that? Well, I guess the advantage of doing that is that at the bottom here, I didn't actually have to go through and count how many positive tests I got. I just did the sum of that column, and that would tell me how many positives I got. I got 11 of them. Well, what you got to be careful about is that a couple of these observations are actually 0. So even though there's 30 observations in this data set, as far as the sign test is considered, how many observations are there? 28, because I got to throw out this data. The actual zeros, the 2 of them, I got to throw those out. You don't count towards our data set. I don't know as though we'll need column C, but yeah, maybe copy it over anyways. So let's copy this data and paste it into StatDisk. If you need to, click the upper left-hand corner, or I guess you can always do the toggle thing, and paste the data into columns 1, 2, and 3. Pretty much think we're going to need column 1 and 2. So we're going to test for a median difference. Now this data is paired data. It's reported height and actual height for the same person. So that data is matched pairs. You could do this with the stuff that we did in section 9.3. You do analysis, then hypothesis testing, mean matched pairs, but that's not what we're going to do. That test requires certain assumptions that we're not making right now. Instead, we'll go down to sign test, and then this time, given pairs of values, because we actually have the data here. So given pairs of values, let's run through the work for a hypothesis test. So step 1, H0, HA, the median difference is 0. And what that means is that half the time people overestimate, half the time they underestimate. Now what you're really not seeing is that really that eta equals 0 means the median for the first data set and the median for the second data set. When you subtract them, you get 0. Or that median difference is what it's called. Median difference. So if half the time you overestimate, half the time you underestimate, you should get a median difference of 0. Let's see what happens when we do our hypothesis test. We'll do that at alpha equals 5% level. And step 3 is going to be input the data. That's good. Now our hypothesis test here is going to be different than it was with the previous one. With the previous one, because we had a small amount of data, we actually had to do a hypothesis test based on table 7, table A7. But if you have a larger set of data, something greater than 25, then you can do a z-test. And that z-test is a nice parametric test. You've turned this into a z statistic, so we can calculate probabilities. We can even get a p-value. But unfortunately, StatDisk doesn't give you a p-value here. So I have to teach you how to do things old school. And doing things old school, it's going to look like this. We're going to be basing things off of a normal distribution. And we're going to calculate a test statistic. And we're going to compare that test statistic to specific values. Now, what we want to do is we want to set up a rejection region and a fail to reject region. And we're going to do that so that we're going to set these values for our reject H0 and reject H naught, and then fail to reject H naught. We're going to set up these values so that there's only a 5% chance that you're going to land in either tail if the null hypothesis is true. And then we're going to see where we land with our test statistic. So those values are actually going to be calculated for you from statistics, and they're going to be based on your alpha. Now, if alpha is 5%, these values are going to be about 1.96 and negative 1.96. But again, those are going to be calculated for you. Let's see where our test statistic actually lands. So given pairs of values, we have columns 1 and 2. We're looking for the median difference. And bam. It calculates some test statistics for us, and then gives us our Z statistic of negative 0.944, etc. So where does that fall? Well, you can plot it out in your mind if you want to think about the critical values, but it's a little easier just to look here. The critical values are in red, and the test statistic is actually in blue. So what's our decision here based on our test statistic? Are we going to reject H naught or fail to reject H naught?
Fail to reject.
Fail to reject.
Yep, fail to reject. Thank you both. So fail to reject. It fell like right there. So that's a fail to reject. Okay, fail to reject. No big shakes there. Can't always win them, but there's your conclusion. Now, kind of an interesting thing to see is, well, what if we were able to actually do this with a parametric test? In this case, you know, it might be reasonable to think that we actually satisfy the conditions to do that parametric test. So let's, for giggles, just take a look at what happens if we try and do this with a parametric test. So let me go back and click Analysis, Hypothesis Testing, and then Mean Matched Pairs. So we're going to do this like we did in section 9.3, but assume that we have enough data so that the differences are distributed normally. Select columns 1 and 2 for our mean match pairs, and bam. Now this time we actually get a p-value, but in order to kind of compare these things apples to apples, I want to take a look at the plot. What's our decision this time? Are we going to reject or fail to reject? Take a look at where the blue value is compared to the red values.
Fail to reject.
Yeah, it's still fail to reject, but the one thing is that it's gotten a little bit closer. I think I have, yeah, got it here. So if you take a look here, our test statistic for this one wasn't as close to the rejection region. Here, you're getting kind of close to the rejection region, aren't you? Here, you're getting like, you know, if it was just a little bit more, we'd probably be rejecting H naught, right? And what is it that measures that little bit more, or how close you are? It's the p-value. In this case, the p-value was 0.09. Let's take a look back here, results. Typically speaking, we need a p-value that's less than 0.05. So close, but no cigar. All right, so in this case, both of these lead to the same conclusion, that you fail to reject H naught. No big deal. With parametric, with non-parametric tests, sometimes it's hard to reject H naught. It's just going to depend on the number of observations you have, and you know, if there's a strong preponderance of one versus the other. How are we looking on that one? Doing okay?
Yep.
All right. I think I've got one more that I want to look at. Let's do this one for matched pairs. So this one's kind of nice because it's not something you can do with a parametric test. You've got 362 positive signs and 383 negative signs. Where do these signs come from? Let's read the problem. It says, assume that matched pairs of data, all right, so that's cool, matched pairs of data, from a poll on internet users who were asked if they make travel plans through the internet result in 362 positive signs and 383 negative signs, and 38 ties. Now, what's going to go on with those 38 ties? Those 38 ties are kind of like a zero. That gets thrown out. So what that really means, you're going to be throwing out about 5% of your data. You know, that's just the price you pay when you're doing a sign test. But you can't do this test in a parametric way. So it's nice that we have the sign test. So we want to test the result of the second variable subtracted from the corresponding value for the first. Use the sign test with a 5% significance level to test the null hypothesis of no difference. So they actually wrote it a little bit different than I might. They wrote mu1 equals mu2. And aside from their choice of a Greek letter, the problem with this one is that they're using mu again. Remind me, what does mu represent for us?
Population mean.
Yeah, population mean, thank you. So, in any case, they give you 4 different options. Obviously, you're not going to choose this option because that doesn't have a quality in the null hypothesis. These are left tail and right tail tests, or excuse me, this one's a left tail test, and that was just a different left tail test, just a different way to write the null hypothesis. So the correct one is the equal to and not equal to. You could also write eta is equal to 0 and eta is not equal to 0. Eta equals 0. That is a median difference. It's equal to 0. And then not equal to 0. It was given to us that we're going to do this at the 5% significance level. And for step 3, they actually gave us the data. The number of positives was 362. Number of negatives was 383. Now, just kind of a gut reaction here from you. Does there seem like enough of a difference to say, oh yeah, it's definitely more in favor of the negatives? Or is it kind of like, more like the center? It doesn't really sway you away from the fact that you're in the middle, that half the time you're going to be above, half the time you're going to be below 0. What's your gut feeling? Are you going to be rejecting H0 or not rejecting H0?
Not rejecting.
Okay. Brooklyn thinks we're probably not going to reject. What do you think? Someone else. Cast your votes. No one else has an opinion?
Reject.
Reject? All right, cool. I appreciate that very much. Thank you. Let's find out. So step 4, we're going to input the data. And we'll put that into stat disk. This is going to result in a z value, but we're not actually going to get a p value out of it, not from the sign test, not in the output the way you have designed it. I'm kind of surprised. It'd be pretty easy to give a sign test, but maybe it's results you just want you to be able to get for yourself. 5% significance level looks good. 362 positive, 383 negative. So, bam. But it might be hard to decide if you're going to reject or fail to reject from here. So what can we do? What should we do, maybe?
Look at it.
Yeah, look at the plot. And what's the plot telling you? What
Fail
should
to reject.
Good. Fail to reject H naught. Nice. Nice. So then you can state your conclusion in words. The data fail to provide sufficient evidence that the median, or to reject the claim that the median difference is 0. So doesn't feel like they're too much biased one way or the other. They're kind of playing it straight in the middle. All right. How are we looking with that one?
Good.
Good. All right. Excellent. Let me pause here for a second.